Okay, let's get started, and welcome back to Operating Systems. And today we're going over chapter number 3. Chapter number 3 is all about processes. So this one might be interesting information for some. It might be complicated for others. It's really a programming topic in terms of what processes are and what threads are and how they are used in an operating system. And it's very much a concept of Unix, but I'm going to apply it towards all operating systems. It's the basic concept of how we're running programs, and the concept of the multi-threaded and multi-processing environments that we are working with in modern-day operating systems. So going over the process concept, the scheduling, how to schedule processes, operations on processes, and a little note on scheduling. This is not going to be a CPU scheduling, this is going to be a process, how the kernel keeps track of processes. Inter-process communication, and then communication at client-server type systems, and look at a small brief look at RMA towards the end of the lecture to kind of see how the client-server environment uses processes in that aspect. So what's a process? A process is a running program, if you want to think of it that way. An operating system executes a variety of different types of programs. We have systems programs, we have batch jobs or batch, types of processing. Time-shared systems use user tasks, or they have other tasks that are performed, so that the system itself is shared. So the textbook uses the terms jobs and processes interchangeably. So a job is a process, and vice versa. And a process, my quick and easy definition is that it's just a program that's running. And a program is a process that's not running. It's a program on the computer, an exe file, or something that you've got installed that you're not running. When you double click on Microsoft Word and you open it up, you create a process. Actually, you create more than one process, but you're creating at least a process. Because that's how information is transferred back and forth between the kernel and the user mode in terms of the process communication, and that is how programs are run on the computer. So a process is a program in execution. Process execution must progress in a sequential fashion. So a process includes a couple of different items associated with it, and you might think of a process as a memory abstraction as well. Each process owns its own little piece of memory. Well, it's allocated to it. It doesn't really own it. It gets access to memory, a fixed amount of memory, and inside of that memory we have a program counter, a stack, and we have a data section. We have the program counter because in a perfect world, every process that started would be able to run continuously. Unfortunately, we only have one instruction at a time that can happen on a single CPU. So each CPU cycle can only run one instruction. We can't have running multiple instructions running from multiple processes simultaneously. It doesn't work that way. So we have to keep track of what processes performed what work and what other process is waiting in line who's going to perform other work. And the work is instructions that are being, essentially run through a queue and scheduled for CPU functionality. So the program counter keeps track of where we are in the execution of that particular instruction set. The stack it's a data structure just like the ordinary stack that you'd actually create as a programmer. That stack is keeping track of all of the instructions. So we load all the instructions on a stack and we pop the stack items off as we run them. We keep a program counter to know where we're at, because we're going to run a process for a few minutes, stop the process. Keep a bookmark to see where we left off. Go to the next process, run a little bit of that process, stop that process. Go to the next process, run a little bit of that process, stop that one. We essentially go in like a queue or a circle, round robin, to every one of the processes, allow them to perform some work for a few minutes, stop it, and then basically switch to another process. We also have the data section, which is going to hold the heap memory. May also hold the instructions, the executable code itself, or any data that might be associated with the process. And so this chart here is what it looks like in memory, actually. So out in memory, we allocate from here, we have 0 to some maximum amount of memory that has belonged to this process. And theoretically, other processes aren't allowed to use this. Only the single process is allocated the particular memory. And so on the bottom we have the text, or the instructions. Yeah, there you go. The text which is not in the previous slide, but it's pretty much going to be referring to the text of the code of the executable file. It has to be held somewhere. Then we have the data, which is going to be like all of our variables and all of our memory pieces that we're going to hold for the running program. And then we have the stack and the heap. They're kind of like this. Some people draw them the other way around. I like to put the heap on the top and the stack on the bottom. It doesn't really matter. This is just an abstraction. And this is just taking up memory banks from 0 to some sort of maximum length. And the concept, though, of the heap and the stack growing into each other is pretty universal in terms of how you're going to display that. And what ends up happening is you run instructions, which is probably why I like to put the stack right here and put the heap up here. We are adding stuff to the stack, and we're adding stuff to the stack, and then eventually, we're hopefully going to be popping stuff off of the stack. We have things like, let's say, for example, a recursive function that creates stack entries recursively, which means, say a function that's calling a function. So the one function calls another function, calls itself, and then it calls itself again, and then it calls itself again. If we have that, we have the potential of growing the stack into the heap area, and then we get what's called a stack overflow error. So if you've ever written a program that had like a loop that went uncontrollably, it probably was going to create a stack overflow error, which means you've filled up the stack and it's overflowed into the heap memory. And you basically ran out of memory in that process space because you were calling something, you had a loop that was allocating and allocating and allocating stack entries, but it wasn't popping anything off the stack. It was just popping onto the stack. And a call to a function actually pushes items and creates new stack entries. So a recursive call that makes another call, that makes another call, that makes another. It's filling up the stack, essentially. And you can easily recreate this by creating a standard recursive function and just let it run for about 5 minutes. Eventually you're going to get what's called the stack overflow error. It's going to come out. The other problem you might have, totally unrelated to this first problem, is usually called, the word heap never actually shows up. It usually says out of memory or something, where the memory grows into the stack and it finally finds a limitation, and then we can no longer allocate memory, and we get out of memory errors. Or memory address error such and such, or anything memory related is generally a heap-caused error. Things that cause heap errors is when you allocate using dynamic memory allocation. Allocate, 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 but never deallocate. So normally you would go, especially with C++ in terms of saying a new this, a new that. Every time you use a new operator, you're creating memory, and the memory's coming here on the heap memory. New uses the heap, actually. Delete is the reverse, which you're supposed to delete off the heap. So if you keep going new, 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 you can easily duplicate this problem in a slight program that does a loop that creates new objects, and just start creating new objects and let that run for 5 minutes, and then you'll get a memory out of memory error, or you'll get a memory violation error or something. Some memory related thing was going to come up at you. So, and this is an abstraction, by the way. It doesn't look like this. I don't even know. I couldn't even imagine outside of maybe. I could probably make this a little bit more realistic by calling it virtual memory, or maybe logical memory. I don't know, and dividing it out differently, maybe with numbered groups or something. But essentially, all of this cells, which makes it look sequential, makes it look contiguous in this picture too. It doesn't have to be contiguous, actually. It's just a block of memory that's associated with the process. It's allocated to the process as the process space is what we generally call it. So outside of the memory that processes take up, we are concerned with the process state. Not every program that we execute is always running. There are different states that the process actually turns into. When we first double-clicked on it, it's new. It just hasn't, maybe we haven't run it before. Brand new. Even if we've closed it and started running it again, it still comes out as new. So the process is created, the kernel comes out and creates this. And then now we have an entry for the process. And then we have instructions that might happen when the process is in a running state. It's new, it might be running. It's not always running, which is interesting. It might be waiting. It might be ready. or it might be terminated. We keep track of terminated process so we can clear out the memory space. And this picture is a diagram of all the different process states that you might imagine. So here, it generally kind of goes from new. You can't go to ready without being new. Every process is new, and hopefully every process makes it to termination. If not, when you reboot the computer, it gets terminated, but we never notice. So we have a new that's admitted in, then it becomes ready, and then it could start running, and then become ready, start running. And this is the scheduler that's making it running to ready, running to ready, running to ready. And then we have events that occur, I/O event that might actually happen, and there might be waiting for I/O. So I was going back to the concept of one instruction at a time being executed on a computer. The kernel schedules all of the activity of all of the resources on the computer. So if you have a CD-ROM drive, you have a USB drive, hard drive, anything, it's considered a resource. And we generally have schedulers for all of the resources. And we have a kind of a looping queuing system where everything goes to the CPU first. And then if it needs CPU time, it gets CPU time. If it needs to be directed towards I/O, then it's immediately directed into a different queue for I/O. And it sits in an I/O queue that's related to the I/O device that it needs to access. For example, I/O devices for the hard drive. We're going to be in a different queue than one for the CD-ROM drive or one from another resource that's on the computer. That's how the process ends up becoming waiting. It'll wait for such certain time. If it goes to the CPU, which is, let's say, the traffic cop. Traffic cop says make a left. It might wait to make a left for a while. But if there's an accident on the left, on the left lane, there's an accident on the other side where the left occurs and the left is not possible, then it might come back to the CPU and say, hey, can't make a left. I/O queue is completely full. It's been blocked up for hours. Redirect me. And then that's when the CPU scheduler can trigger a trap, essentially, which is an exception that comes back up to the user mode and say, timed out. We waited. The process waited, but it lost hope. It timed out. So there might be a problem with your CD-ROM drive. Then it might go back and retry it later or something. Maybe it retries it recursively. Who knows? But we end up with all of the kind of coordination happening from the kernel and from the CPU scheduling. And CPU scheduling will be an entire chapter, separate chapter. So the kernel owns this data structure. It's called PCB, or Process Control Block. This is usually a block. It's usually a hash table, a table of some sort that is implemented by the kernel to keep track of all of the running processes. So the information associated with each process is in this PCB. We have the process state, the counter, program counter, CPU registers, scheduling information, memory management information, I/O request, I/O status, accounting information. Everything that needs to be tracked for a particular process is in the process control block. Why do we need that? It's kind of like how people keep address books. Because you're going to forget your friend's birthday, or you're going to forget your friend's name. Maybe, I don't know, maybe not the name, but maybe the telephone number. Yeah. So it's kind of like a history. It's also kind of like keeping the data handy, lookupable. So the kernel does this because it can't remember all the processes that come into the system and where they stopped, what processing they need on the program counter, what memory they own, stuff like that. So it's the kernel's way of getting organized. And here is what it would look like in memory, the process control block. Actually, if I were to draw this out, I'd probably make it more into a table than but this is supposed to represent memory cells. So we have certain memory cells that are associated with the process state, the number, the counter, and all that stuff. And this ... means it just continues on with more information. And this is just a subset of the information that the kernel can carry or store about the processes. The information needed is going to be particular for the process scheduler, for the CPU scheduler, that is very particularly specialized for the operating system. Every operating system has its own design for a scheduler and its own design for process management. What I'm describing to you is something that's several, very generic, several different operating systems. Most of their desktop operating systems work this way. Here's a CPU switch from process to process, also referred to as a context switch. So CPU scheduling is nothing more than taking a process out of the queue, looking up its information in the PCB, allowing it to go and do some work, and then stopping it, putting it back, updating the PCB, starting a new process, and allowing the new process to do some work. And the switching that goes on between, when the first process stops and the second process gets to start, and that one stops, and third, it's called context switching, and it generally adds the overhead to the system. So the speed of the context switching, which is why a lot of people try to implement it in hardware, they try to make it more efficient, because this switching adds wasted time, because you still have clock cycles going on, but what you're doing is you're wasting clock cycles on switching processes around instead of actually running the jobs, running the processes. Because what do we really want? Do we want a system that can juggle 1,000 processes? Or do we want to run Microsoft Word? We want to run these processes, which inevitably is the situation when, let's say, for example, you load up 5 different versions of Microsoft Word, and then you notice, oh, it takes a little longer to go from one version to the other one. That's the context switching speed that you're looking at, actually. Some computers are actually pretty slow at that. Depends on how fast the CPU is working. So if you have a really fast CPU, you can load up 25 different programs. It has nothing to do with the amount of memory that's on the system, by the way. It just has to do with how fast the CPU is running. So imagine it's all like a manual process. Imagine a wheel that spins around, actually. If the wheel spins faster, it can visit more locations more often. So you can do more context switching because it can get more done. So here's process 0 and here's process 1. We have 2 running processes. And here's the operating system's control over that. We have executing here. So we have an interrupt or a system call, and you want to save the process, which is basically the concept of CPU switching, context switching. We have a call that says save the state of the PCB entry for process 0. Reload the state for process 1. Let number 1, this one over here, run. Save the state, let number 2 run, and then we're idle in here. We were running, we stopped, this is the switching cost that I'm talking about. This is what slowing down the performance of your computer is, this expense in the time it takes for these instructions to be performed, which isn't really that much if you think about it, actually. But you're constantly going from one process to the other process to one process to the other. You're flipping back and forth. Just add another 10 processes in there. These guys could be waiting for a while. So there's different ways of designing the CPU and the scheduling technique, different algorithms, and I'll talk about that in an entire chapter on CPU scheduling. But the context of the concept of switching is an important one to kind of get out of this lecture. And the processes are running, they're constantly being switched. They're constantly being told to wait or sitting idle while another process is running. And then we have process scheduling queues. So we have different types of queues. We have jobs queues, ready queue, device queues. If we take the abstraction of, we have CPU bound processes, they're waiting in one queue. We have I/O queue bound processes waiting in another queue. We divide the work out so we can maximize the amount of minimize the amount of switching, maximize the efficiency of the CPU. As an example, if we have a job that is, purely, let's say it's using the math coprocessor in the CPU, and it's not doing anything with I/O or anything like that, we could throw it into the CPU queue automatically. If we have a process it's a high I/O intense process, then we'll directly, instead of going to the CPU queue, we'll direct it out to the I/O based queues. If we do that, then we don't have jobs sitting in this huge CPU queue waiting to be run that only need a second or so. But what they really need is the I/O. So we'll let them do the I/O first. While these other ones that need CPU time, they can do the CPU. They can have the CPU right now. So it's kind of like sharing, sharing the workload among the different resources. So by definition, the job queue is a set of all processes in the system. The ready queue is the set of all processes residing in memory that are ready and waiting to be executed but haven't had any chance to run yet. They're just ready. which is the case of everything that starts up in the beginning. And then device queues, set of processes waiting for I/O devices. Processes migrate from these various different queues depending upon what they're doing, essentially. So here's the ready queue and the various I/O queues. We have it's kind of looks like a linked list sort of. I got the head queue, the tail queue. We got the ready queue on the top, and then we have, this is tape 0, tape 1, disk, terminal. These are different devices. So these are I/O queues. And here we have process control blocks, maybe that are set up for each one of the different queues, which is, going back to the PCB concept. The process control block is keeping track of the number of processes that are running and the information about those processes. It makes sense to have different process control blocks for different queues. If you separate the blocks out, then there's less of a search space in the table itself, and you only have processes in the table that are associated with the queue. So it's easier to schedule those processes, because the concept is put it into the PCB, run it, leave it in the queue for as long as it stays in the queue. It has an entry in the PCB. When it leaves out, it leaves out of the PCB. And you're just going back to the PCB and you're going, okay, what's the next process? You? Okay, here, you run a little bit. Oh, you're done? Okay, get out of here. Erase them from the PCB. Keep going with the next process and the next process. So if you keep them separated out, and you can have any number of queues. You can have more than one queue for the same device if you wanted to. You can create multi-level priority queues, which is quite common. So the kernel has a different queue than the user mode, or maybe there's different levels on the user mode queue. So in that theory, what ends up happening is you can set priorities, you can set all sorts of different specialized configurations, different levels of PCBs that are associated with the queues. So, because here's an example. Here we got the terminal only has one, but the disk, it's got, maybe we have many different disks. Maybe there's 5 or 6 different disks. Maybe this is all for disk 0. Who knows? So the representation of the process scheduling. So here is a kind of a picture of what I've been trying to describe in terms of CPU, and I call it CPU scheduling because that's what it really is, actually. Process scheduling, PCU scheduling. Okay. Well, theoretically, process scheduling is CPU and I/O. So we have a ready queue. Everything goes into the ready queue in the beginning. It goes to the CPU. CPU says, it's an I/O request. It's a fork of a child. It's an interrupt. It's a time slice. It's one of these items here. If it's an I/O request, for example, then I'll go, get out of this queue, go into the I/O queue, and then wait for the I/O to become available. Because hardware and I/O devices, they only let one process at a time touch them. So they can sequentially queue up all of the work that needs to be done and then just constantly run to get all that stuff done. If it's a fork a child, then execute a child, and then go back and get back into the ready queue. Everybody goes back up into the ready queue when they're all done processing. Well, think of it sort of like a flow chart. You come from CPU, you go down to here, interrupt occurs, okay, you go back up here, you go down here. It's like a bunch of ants working together, or separately, I should say, with shared resources, and the goal is essentially to process all of the work that they need to get done. So schedulers. So this all has to be scheduled. And another word for scheduling might be orchestrated, or it might be planned or routed. So scheduling is kind of a generic word term that's used for creating this map, this schedule, for how the work is going to be performed. So schedulers, we have different types of these schedulers. Long-term and short-term as an example. And we also could have a medium-term scheduler where jobs go from short to long. They go and end up hitting a medium in between, which is kind of an extension on this. So the long-term one is the job scheduler. It's the job queue. So it selects the processes that should be brought into the ready queue that are essentially all processes in the system. If a process gets built, it's automatically in the long-term scheduler. And then we have the short-term scheduler. Those are the selected processes that only need CPU time. So, or CPU scheduler. You might want to call it a PC. The short-term scheduler is the CPU scheduler. You can do it that way. Select each process should be executed next and allocate CPU time to it. So they're here. Long-term scheduler is everybody. Short-term is just getting to the CPU. Because you're not going to give too many CPU cycles for each process. So short-term could be just waiting for 1 or 2 CPU, small little CPU bursts. And they actually call them bursts or cycles, which is representation of time in terms of a unit of time. Would be a burst. And a burst could be like 20 clock ticks or 100 clock ticks or something. The speed of your CPU is going to determine how big your burst sizes should be and how many of them you should have. But who really picks that out? Instead, the manufacturer of the operating system says, you need at least a Pentium such and such, and you need this amount of memory, and you have to have this size hard drive, which sets the basic minimum requirement that the operating system needs for an optimal scheduler, for an optimal disk allocator, for all of the different built-in data structures that it needs to create and use. So, of course, if you put a faster CPU on there, it's going to work faster, by theory, hopefully. It may not, depending upon what kind of scheduler. A CPU scheduler can make a fast CPU run very slowly if the scheduler is not doing its job correctly. So here's the addition of a medium-term scheduler. So what we have going on here, we're swapping in, swapping out, partially swapped out processes. Go in, partially swap it out, go to the CPU, get some time. If not, go back into the ready queue. Go to the CPU, go to I/O, come back into the ready queue. So between the I/O requests and the CPU requests, between the long-term and the short-term scheduler, the medium-term scheduler can be put in there sort of like a ready queue. You say, okay, we haven't gone back to the long. We're going to go back to the short any minute now, but we're sitting in the medium as a ready queue. And then depending upon how many jobs are in the system, the algorithm can be optimized essentially to get rid of the medium scheduler. Because if you think of the concept, if you break it out into 3 groups, but you only have like 2 processes running, you're only going to have 1 process in each group. Why should that processor go from long to medium to short when it should just go to short? Skip the medium altogether with. So, and then actually that's kind of an interesting thing with queues too. If you don't have that many I/O devices and all the processes are going to the same kind of queue anyway, why break it out? So, because you just got to go to. It's almost like the routing's got to stop at make unnecessary stops, and the stops add to the context switching time. So. Okay, back on the lecture stuff. Short-term scheduler is invoked very frequently. Milliseconds must be fast. Long-term scheduler is invoked very infrequently. Seconds, minutes. And this is the degrees of milliseconds, seconds, minutes. It's relative. It's usually in clock ticks. It's how many seconds or how many clock ticks per second, and then judge that out. Short-term is meant to just go to the CPU, which means we're going to send all the short-term jobs. We're going to process those guys first because they're theoretically not going to take up as much time as everything else is. So it's like first in. It's not, instead of doing like a first in, first out, it takes a fastest to complete job first kind of thing. And in theory of making that short means get all the short jobs out of the way and then take the long stuff and spend a little bit more time with it if it's going to take longer. The long-term scheduler controls to the degree of multi-programming. It's multi-programming, multi-processes running simultaneously on the computer. So if you've got a long-term scheduler that's really, really slow, you really have the impression of only one thing running. Especially when you go to click on another window and it's very unresponsive. In fact, that's another interesting thing you might notice, maybe not. If you open up like 5 or 6 windows, actually Windows, Microsoft Windows, XP, I can only verify this for XP because they're using a multi-leveled scheduler with a short, medium, long kind of configuration. If it makes it out into the long-term scheduler, the window will take longer to open. So you open up 10 programs, you switch between 2 a lot, and they load pretty fast. You go to one you haven't loaded in like the last half hour, you might notice it takes a lot longer to load. It's moving through the schedulers and it's coming up to the front of the queue. It's been backlogged, it's been pushed away from processing, because why have it in there if you're not using it? If it's minimized, it's been minimized for like the last 10 minutes or something, it's made its way out farther and farther away from actually getting CPU time, then it means you're using something else, and something else is getting a higher priority on the CPU at that time, which means the current window that you're working on should run as fast as it could run, and nothing else in the system really matters at that point. If you think of these programs as processes, that's the effect that you'd actually experience. Long-term scheduler controls as real multiprocessing. So processes and you can experiment with that by opening up Windows. Let one sit for a half hour. Sometimes you click on it, in the older systems, you clicked on it and it kind of like partly painted, and then it kind of sat there. Sometimes it said waiting on the top. It's like, well, what are you waiting for? Because you're in the long-term scheduler. We thought you went away, but we still haven't deallocated you. You're still in memory, and you're still a running process. But you just haven't gotten any time to run because you're not high priority. So. Processes can be described as either I/O-bound processes or CPU-bound processes, as I've mentioned already. In the I/O scenario, it spends more time doing I/O than it does computations. Many short CPU bursts is what it gets. Many small little short, but it's mostly I/O bound, so it should get more I/O. CPU bound processes spend more time doing computations. A few very long CPU bursts, because we want the CPU bound processes to finish. Otherwise, we got to schedule them. We got to context switch them, and context switching adds overhead to the system. If it's for the CPU, let it run longer, and give it fewer bursts. If it's an I/O, come on up, get your bursts, go away, go back to your I/O device. Okay, in another 5 minutes, come on up. Here, we got another thing for you, and then send it back to the I/O device, reroute it. So. You don't have to spend, if you have the same amount of time, which is kind of interesting, older systems used to use an equal amount of time. Actually, older systems had the same amount of process space allocated to each process. Now we have different variations going on now. But older systems used to have every process got the same amount of CPU time than they did I/O time. Then you'd have a process that came up that was really I/O bound, that needed 1 or 2 clock cycles to run something. Ran it, and then you get that CPU sitting there, the light's on, but nobody's home. It's sitting there waiting for the rest of the burst to happen. It's taking a break, essentially, because the process didn't need that much time. But then if a CPU-bound process shows up, and you only give it 1 or 2 seconds, you're in trouble. So it makes sense to kind of divide out the processes by I/O or CPU and adjust the burst times for the usage so that one gets longer than the other. So people might think, oh, it's not really fair. It's the thing, it's like, why give you that much if you don't need it? It's wasteful in terms of processing time. It's also wasteful to have one queue. Divide you all out into different queues. Why should you all have to wait? You know, some people might be able to run faster in a different queue. And the concept of context switching, as I mentioned before, is taking one process, giving it CPU time, and then taking the process away, updating the PCB, putting the process back into the ready queue or whatever queue it belongs to, and then finding a new process, going through the PCB, picking out a new process, and giving that CPU time. That's context switching. Doesn't sound like it, but that's what it is. So when the CPU switches to another process, the system will save the state of the old process. That's the program counter, essentially, that's being saved. And load the saved state of the new process. And you're wondering, why do I want to do that? Otherwise, we'd have sequential processing. What we're looking for is, multi-processing. In order to accomplish multi-processing, we need context switching. If we didn't do context switching, it would be like the DOS prompt. One program would run, and then another one would run, and then another one would run. Like before Windows, we didn't actually have to deal too much with context switching. Although we still had context switching back in, I meant to say DOS. Back in the DOS days, we still had context switching because the DOS operating system, the disk operating system, needed to do stuff to prepare the user environment. We still had the user environment, we still had kernel mode. And we have kernel running processes and user running processes. But the abstraction that you were seeing was just one user process running at a time. You ran a program and you waited for that program to finish. And then if you're a Unix person, you know that Unix is not sequential like the DOS environment, because you can have foreground, background processes, and you can have daemon processes and all sorts of different things that you could never accomplish with a DOS prompt. And still can't accomplish with a DOS prompt. Because the concept's different. It's the way the interface is processing your commands. And your commands are the processes that are being created. So context switching time is overhead. If you walk away with anything today, remember the speed of your system is controlled by the speed and the efficiency of the context switching. Doesn't matter how fast your processor is. If your operating system is not doing proper context switching in an effective way, you've got a slow computer. Because the operating system is giving you the abstraction of how the hardware is working. System does not do anything useful while switching. So time dependent on hardware support. Which is why there's been so many experimentations putting in hardware controlled context switching. You can have a hardware stored PCB, hardware implemented queues, all sorts of different things that can be done from a hardware level that are aimed at making the context switching faster. Faster is what you want to do it. Do you hear noise? Like a movie or something going on. Alright, process creation. Now I got you all listening. Before you were asleep, now you're awake. What? Process creation. The parent process creates a child process, which in turn creates another child process with another process, which forms a tree of processes. So we have a process tree that's created. That gives us resource sharing. So remember that little picture right here? I'll go back to it for a few more slides here. We had in the beginning a picture of what a process looked like in memory. Here it is right here. Every time we create a process, we get this. When we create a child process, the child gets a copy of this and it's inside of this. So the parent actually stops running, the child starts running. And the child shares the same resources as the parent. Which is kind of interesting. So child processes are nested inside the parent process memory space, which is why a child is different from a parent. If you want, you can create two separate processes that are going to be held separately, which is essentially an interesting concept to kind of think about, because when you double click on a program and you bring it up, you really only have one process running. The program, the exe, actually created a process. When you create a process in your process, it's really a child process. So in terms of resource sharing, the parent and the child share all of the resources, which is that memory space I just showed you. The child shares a subset of the parent's resources. It's kind of a snapshot of what it looked like when the child was created. Parent and child may also share no resources, depending upon the implementation. These are not exclusive events, and these are not simultaneous events. These are just examples of how resources might be shared. There are some operating systems that don't have child processes sharing parent process memory space. There are some operating systems, such as Windows, that doesn't even allow you to create a process. That the operating system, the kernel, is the only one that can create a process. User mode can't even create a process. In your Linux systems, 99.9% of them have the child sharing the parent space. It's just a way of organizing the process. In the older systems, System D, and some of the older HP systems, HP UX, I believe, does it. It has separate process spaces, and then we have one thread per process, and I haven't talked about threads yet, but we have different threading environments. We can have multiple threads that share one process, multiple threads that are mapped to only one process, vice versa. Many processes that are mapped to one thread. Threads are kind of a sister topic to this, which is the lecture 4, actually next week. But execution, the parent and the child execute concurrently, but only one of them runs at a time. So if the parent's running, the child's sleeping. If the child's running, the parent's sleeping. The parent normally waits until the child terminates. So if you're a parent and you create a child thread and the child thread is running, you're waiting. and you get woken up with a signal that's generated when the child terminates, goes away, sends a termination signal back up to the parent, says, okay, parent, you can start running again. Why do you want to do that? Well, one of the first assignments for this course, actually, is to create a shell. And your shell is multiple processes. We have a process that we bring up to create the shell. And inside of the shell, we pause the shell. Think of it like a DOS prompt or terminal prompt in the shell, which is what your Windows system is actually. It's just a GUI shell. But in theory, what ends up happening is the shell goes away for a second while the child process runs. Child process might run in the form of a program, or a command, or an instruction. And then when the instruction ends, the control comes back up to the shell, which is a multi-threaded shell environment, which is what you'll be creating in one of the assignments for the course. In terms of the process creation, we have the address space. The child gets a duplicate of the parent, and the child has a program loaded into it normally. You fork a child because you want to execute some work. You're a shell, and someone says, I want to run ls. I want to run a command. So you have to fork a process, which is essentially what goes on in the background. And the process becomes a child of the shell, and the process runs the command. And then it executes it, and then it comes back up to the parent. Can you have the parent just do it? Sure. You can configure it that way. In fact, that's what you're doing when you're programming in a Windows environment. The abstraction of the multiple threads programming from a user mode perspective is missing. You don't have that. You just exec it, or system, we run a system, and then we give it the name of the file, and it can run it. And behind the scenes, it's really creating a thread, or it's creating a process that's a child process to run it. Because always when the execution ends, it comes back to the parent. You're back to where you left off, hopefully. Here's the Unix example. The fork is used, a fork system call, to create a new process. Exec system call is used after a fork to replace the process's memory with a new program. So we exec, and what was this? Exec is kind of like a fork, but it's lightweight. It doesn't even create a copy of anything. It's just used to run a program and then come back. And these are the commands you're actually using in the assignment. Actually, maybe at the end of today's lecture, if I have internet access, we'll take a look at some of the assignments, because we haven't done that yet. Process creation. We fork. We have a parent. Parent's going to wait. We fork. We have an exec. We exit. We go back to the parent if we have a child. So we just have one process running at a time, though, in that memory space. We don't have multiple running processes within the same process space, because it's all sharing the same memory. They would fight with each other. They would have definitely arguments associated with the memory. Here's a C program that creates a process. So we have PID, it calls our process ID. When we create a process, all we get is a process ID. We don't even know what the process ID is. And we don't even know what the process ID is, because instead we get, did it come back okay, or did it come back as a failure? So we check the return value, and we say, if it's 0, oh, we created a process. And then the process ID goes back to the shell, which is why you can type in PS for process or jobs and get a list of all the process IDs in the shell, of all the child processes. So the parent always knows about the child process IDs, but it never knows about its own process ID, which is kind of weird. Only the person above you, the kernel, knows about your process ID, which is why you would have to run a system call like PS to get process lists, to get the IDs of all the running processes. So the code is pretty simple. It's just checking on the process ID. If it's less than 0, we have an error, print out fork failed. If it isn't, print out a child. The child is going to be used. And this is used instead of the fork. We have exec. There's an LP, XC. There's several different variations of this function call, and it's because we have a different parameter list that we can give it. This is running ls, which is like dir in DOS. Else, the parent will wait for the child to run. When it's complete, when the child exits, it gets a signal back, and then the parent continues to run. So that's actually in the textbook as well. So you'll be able to get that out of there. So here's a tree of the processes on a typical Solaris system. And you see the process IDs here, 0, 1, 2, 3. You're never going to see numbers this low in the user mode. Init is normally 1. The scheduler, or the kernel, if you want to call it from that level of abstraction, is 0. So once the kernel loads up, because then you have to think everything in the system is a process. Even in a Windows environment, everything is running in the form of a process. So after the kernel loads up, when it loads init, which is the user mode, you get process 1. And then you're going to get process, somebody logs in 251. You get a huge jump in the numbering system because you have some reserved for kernel level processes. So kernel level stuff is really low in the number scale. User mode is really high in the number scale, actually. And every time you invoke a new process, you get a new process ID. It's always incremented. It's always higher. And most systems don't reuse the process IDs, which is interesting. So flush, page out. These are other different kernel level. These are other different kernel level processes that respond. So you can kind of see how the numbering here. We got 2,123. It can go up as high as it wants to go up. And the process number doesn't really mean anything. Every time you run anything, you're always going to get a process number. This is kind of interesting. They don't give you process IDs if you're in a Windows system and you press Control Alternate Delete and go up to the Task Manager and you look at running programs. I can't remember what it's called, but there's an option in there to see a list of running programs. You'll never see well, maybe you do see the process IDs. But what you're looking at is a very similar thing than if you were a Windows, a Unix prompt, and you typed in PS or jobs. You're going to see very similar data, where you're seeing a list of the processes that are running, the names, who owns it, what its ID is, how long has it been running, all the information about the processes that are running, which is the same concept in Windows. In terms of the process termination, the process executes the last statement and then asks the operating system to delete it by going exit. So exit is actually a system call that says close me down, which means take me out of the PCB, take me out, deallocate my process space, clean me up, get rid of me, exit, which is what the operating system should do, otherwise it's creating garbage. When you have processes that terminate unnaturally, they don't signal an exit, then you still have pieces and bits of the process still out of memory, still allocated but not deallocated. You still have an entry in the PCB. The scheduler still thinks it's alive and it's still giving it CPU time. And your system will run slower. And how do you do that on a Windows system? Load up a bunch of stuff, like 5 or 6 different programs. Get one and do something bad with it so it gets hung. So the system screen says waiting. And then notice how the speed of your computer goes down. Because it's still allocating time for those programs that are hosed. And it's still allocating memory. And if you have a lot of that stuff loaded, your system's going to run a little bit slower than it would be if you didn't have all that crap still going on. So it's best to get rid of that stuff, reboot the computer if you want your system to be back to normal. In fact, that's the kill or the terminate. Most people go Control-Alt-Delete, they go up into the Task Manager, they look for the system program, and then it usually says something like, unreachable or waiting or hung or terminated or, I don't know, some indication that it's not healthy. And then you click on it and you get rid of it, which is kind of like doing a manual exit or termination on that process. I'm sure you've all done that before, if you're Windows people. Because Windows has a tendency to have malfunction processes occasionally. More so than any other operating system I've ever run into. Okay, so output the data from the child to the parent via await. So the parent waits, then the output from the child comes back up to the parent, and the parent's done waiting. The process's resources are deallocated by the operating system. The parent may terminate execution of the child process using an abort. You can abort the child, basically doing early termination without the child terminating on its own. And the child has exceeded maybe perhaps allocated resources. It might be good to abort it. It's not doing what it's supposed to be doing. The tasks to assign to the child is longer than required or needed. The parent is exiting. You want to kill the child so the parent can exit. So you abort everything. Some operating systems do not allow child to continue if its parent terminated. And all children terminated processes have what's called a cascading termination, where if the parent terminates, you cascade down to all the children, or vice versa. Which is what should happen in a perfect world, because if you started a process and the process was allocated resources, and you have child processes that are running and the parent goes away, well, when the child exits, he has nobody to signal to say that he's gone, which means his resources will never be deallocated. So then you have memory leak going on again, because you have space that was allocated that's reserved, but it's no longer being used because it can't be deleted, because there is no parent to take the command from to say, it's okay, clean up your mess, and we can take you out of memory, you're all done. It doesn't work that way when the parent goes away. They also can be concerned with some of these things are actually done on purpose. As an example, a print queue, some like daemon processes that go out there and they do things. They don't really have a parent. So you start up the process, you fork a child, the child goes out there and acts like a print queue, or it goes out there and keeps constantly checking each one of the ports for activity, and then signals a message if activity is found. And then parent dies, goes away. So there's no way, really, of getting at the child, and there's no way of the child leaving or exiting. So the child's just going to run forever, but sometimes you want that. If you have a port sniffer, you have a print queue, you have something that you just want to run constantly, but you have no interface to it and no need to touch it, no need to manually control that process. It just runs like an automation, then, or daemon. Then it's perfectly normal to exit out of the parent and leave the child process running. So sometimes referred to as orphaned processes. When the parent goes away, it creates an orphan child. And the orphan child is stuck, can't terminate. Well, it can terminate, but there's nobody around to signal to say I've terminated. So nobody catches the signal and nobody cleans up the mess. So the memory is still allocated. Cooperating processes. Just like people, processes are kind of like people. Some of them don't get along. Some of them are independent and some of them are cooperating. So independent processes cannot affect or be affected by the execution of any other process. They're in their own separate little process world, their own little process space, and they just do their own work and mind their own business. They go to work, they go home, they don't do anything. So they don't cause a disturbance, hopefully, for the rest of the system. And then we have cooperating, or processes that work together, so they can affect each other's space because they're sharing memory. And so they can overwrite what someone's doing, they could not cooperate well. Or they could process a bunch of work, and all of these processes are working together, and they can get a lot more done than a single independent process could, possibly. So you have more processing power, essentially. Advantages of the process cooperation: information sharing, computational speed up, modularity, and convenience. So let's go back to CPU scheduling for a few minutes. We have one single independent process. It's working on its own. It's going to get the same amount of CPU time maybe as every of the other processes that are out there. And then we have tons of processes that are all working together in a process group. Well, the whole group could be allocated at a higher priority, or could be allocated time differently than a single independent process if it's configured correctly. And so we can give more processing power to the cooperating processes, perhaps, and make it more efficient. So all that work can get done together and get done a lot faster than an independent process that might not be having as much work to do. Also, if we configure it correctly when we make the processes, we can have cooperating processes that are sharing the same memory space. Makes it more efficient than all of them having the same copy. It's kind of like, the whole thing with Google Docs as an example. If you put something up on Google Docs, you can have 2,000 people log into it, or 200 people log into it, and they can all make changes to the same Google Doc. I don't know, is there a limitation? I don't know if there's a limitation on how many people can log in, but you get the point. There's multiple cooperating processes logging into it. If you sent the same document out to 200 different people via email, And if everyone edits it, changes something in it, you got 200 to cooperate copies of different documents that they've changed to incorporate into a single master. More work, more power. So if you're all sharing the same memory, which is in the case of cooperating processes, and that memory sharing allows for more efficiency. You don't have to go back and edit the whole thing. Everyone who edits it together as a group. You have an evolving document, theoretically. Although I have logged onto some Google Docs that people cut and paste and they delete half the document out of there. I don't know what happened. Defeats the purpose when you get people who just think it's just a copy and it's just not an accumulation, and they're just going to take off everything except for what they're looking at, their part of it or something, and delete all the other stuff as if it's their own document. It's like, okay, no, it's not your own document, it's a shared document. So. Which brings up the concept of consumer and producer and the classic inter-process communication. Let's say we have a bunch of processes sharing a piece of information. I think we have a bunch of processes who are logging on to Google Docs and they're sharing a Word file or an Excel file. In this particular scenario, we have a classic issue that comes up. The paradigm of cooperating processes. We have a producer process that's producing information that is consumed by the consumer. So maybe not really a good Google Docs thing, but let's think about copying a file from point A to point B. And let's say we have two processes that are doing it, which you can accomplish with a producer and a consumer. You have one process that's going to open up the A file, and maybe it's going to have a shared buffer between the B file. And another process is going to, the first process is going to open up file A for reading, and it's going to read the bytes from file A and copy it into the shared buffer. And then process number 2 is going to open a file for writing, and it's going to write out the shared buffer to this brand new file that you're copying it to. And this is basically how the CP command works, or copy commands. Copy this file to this file, as an example. And change the location. So we have a couple of choices. We can have a bound or we can have an unbound buffer. We have this buffer space that's between A and B. And the buffer space can be a circular buffer, it can be bound, it can be unbound. And the way we configure it is essentially how many bytes and how big do we want to make it, and how do we want to orchestrate the reading and the writing to the shared buffer, which is the producer-consumer issue. So unbound buffer places no practical limit on the size of the buffer. It just says the reader can read in as much as they want before the writer starts writing it. The unbound buffer assumes that there's a fixed size, so the producer will produce to a certain point, read to a certain point, and then when the buffer fills up, stop and allow the writer to write out, hopefully. One process at a time is normally running. And the situation that comes out with the consumer and the producer is supposed to produce items that the consumer is consuming. And lo and behold, what ends up happening is the consumer tries to consume items that don't exist. Or the producer doesn't produce anything because the consumer is busy consuming, and it's not able to produce anything because the consumer's running all the time. And then the buffer ends up becoming empty until the producer decides to start producing items again. So it's shared cooperation between the two processes. So we have shared data in this particular example, and if we were to program it using C, actually, in here we have define with a buffer bound solution, where we have a shared memory solution where we've got a bound buffer of 10 bytes. And the solution is correct, we can only use the buffer size -1 elements. So it's kind of slow. Load up 10 at a time, consume 10. Load up 10, consume 10. So you can make it bigger, optimize it a little bit. This is for the bound size. With the bound size, the producer produces until the buffer is full and then stops. And then the consumer empties it out until it's empty and then stops and tells the consumer, okay, read more in. And it's kind of like how you putting out a fire with a bunch of buckets. You send the buckets one direction all full of water. And they all get empty and then they come back the other direction. And they get filled up with water again and they come around this way. And it's like a circular buffer. where you're circulating the buckets, and along the line, some of them are getting filled and some of them are getting empty, essentially, which is what you're doing with this shared buffer. You're filling it up and you're emptying it out. And that's a form of what's called inter-process communication, or IPC. And there's about half a dozen of these scenarios. There's the reader and the writer, the banker's algorithm, dining philosophers, producer-consumer. There's a lot of these different scenarios, and they all represent either a deadlock, a starvation, or a resource sharing, intense resource sharing environment, or any environment at all that requires more than one process to communicate with each other in a shared effort environment, shared work. So inter-process communication is the mechanism for processes to communicate and to synchronize their actions. We have a message system that might be invoked, and this is where we get the kernel support. So some operating systems like Unix and Linux have kernel support for IPC, and they actually support process programming. Some programs or operating systems like Microsoft Windows does not. So you can't do any of this, and there's no kernel support in Windows for inter-process communication. It's a different type of programming, actually. So a lot of people think, well, Unix is more grassroots-like, because you have a lot more control over some of the kernel features than you do in a Windows system. Depends on what you're trying to do, I guess. So the message system. Two forms of inter-process communication. One is message passing, and the other one is shared memory. So the first one I showed you was a shared memory, where we have that buffer. The second type is the message passing. If we're going to pass messages, we're going to have a send and receive. And we're going to have kernel support. These are system calls. And message passing uses a mailbox system. Actually, each process has a mailbox. I'm going to send the process a letter. Go write a letter, send it to the process. Process receives it, reads the letter, and then responds and does something. Hey, I'm done consuming. Would you like to produce more items into the buffer? Sure, no problem. And it goes out and it produces more items into the buffer. So it's just a way of describing the communication channel between the two processes. Or the flip side of that is that instead of sending messages back and forth to each other, they all look at the buffer and they go, the buffer's empty. The buffer's half empty. The buffer's full, and they judge what they should do based on the buffer. And actually, believe it or not, it's kind of like how people respond in life. If you're sent a letter and you're told to come at a certain time, you will arrive at a certain time, hopefully, if you're following the instructions correctly. Most of these processes that receive messages are going to follow the message correctly. Or the process doesn't think like a human thinks, though. So if a human comes by and sees the building on fire, you're probably not going to come in to go to class. Because you received a message that said class starts at such and such hour. So you were on your way, but you looked at the class and you went, it's on fire. So as a person, you decide not to go in, which would be shared memory. So the shared memory between you and the teacher, I would assume that you would not come in either. I would assume that you would stay outside. Unless you're that desperate to get educated, then you come into a burning building that's set in a classroom while you're on fire. I don't know. Alright, maybe a bad example, who knows. IPC, two operations, send and receive. If P and Q wish to communicate, they need to establish a communication link or channel, and then exchange messages via the send and the receive. So the implementation of the communication link is a physical or logical. In terms of a physical, it might be shared memory, hardware bus. It might be a piece of shared memory in the operating system that says, go to this address and check out what's there, and use that as your mailbox. Or it might be logical, in terms of logical properties. So it depends on how and what type of support the kernel and how it's implemented in terms of the kernel support. And here are some implementation questions to actually kind of consider, because it's really all dependent upon this. How are the links going to be established? Are you going to send messages? Are you going to put up a bulletin board? Send out email? How's that going to work between the two processes? And can a link be associated with more than two processes? Can you have one process that sends a message out to 200 of them? How many links can there be for a given pair of communication processes? And what's the capacity of the link? And is the size of the message in the link can accommodate fixed or variable information in terms of the size of the message. And is the link unidirectional, bidirectional? Are we going to send messages back and forth? Or is it going to be more like a dictatorship where one process tells another process what to do all the time, and the other process says, okay, never fights back? If you think about it, the communication models are kind of interesting, kind of mimics real communications. Here we have A and B scenarios where this is using shared memory and this is using message exchange. So if it looks like a piece of memory, we just change the memory. Then process A looks at the memory here. Process B looks at the same memory here. They're all sharing the same piece of memory. It's not like a bulletin board, actually. You know, everyone goes to the same, looks at the same status update and says, it's still on fire. Okay, don't show up. Versus process A coming through a piece of shared something with process B, another type of communication exchange where it could be a mailbox, a piece of memory. But it's not controlled by the kernel, it's controlled by the processes. The processes are creating that abstraction versus the kernel. You need this on you get this on a Linux, Unix environment. You get this on a Windows environment. If you're going to do anything like that, you're going to implement it yourself. The direct communication is the sending and the receiving of the messages. It's the message exchange. Message passing, which is direct, versus indirect, which is shared memory. So direct processes must name each other explicitly. It's kind of like how we send letters in the mail or email. We actually have to put a receiver on there. We have a sender and we have a receiver. So if you get a message from somebody you don't know, you can throw it away. Or it goes into the spam mail, maybe. So send a message to process P, send a message to process Q. Process Q receives a message. So properties of the communication link. The links are established automatically. Yeah, actually email is established automatically through the server, the shared communication device email server. And link is associated with exactly one pair of communicating processes. In between each pair, there exists only one link. And the link is unidirectional, but it's usually bidirectional. It can be, maybe unidirectional, it might be bidirectional. Email is unidirectional. I send you a message, you read it, you send me a reply. If we were both able to send and receive simultaneously in both directions on the same message, then it would be bidirectional. That would be the case in which I called you on the phone and we both talked at the same time. Together, synchronously, that would be bidirectional. So. Indirect communication, that's our mailbox. So the messages are directly received from a mailbox instead of by the processor. It's kind of like having a P.O. box. You go out to the P.O. box and each box has a unique ID. And the processes can communicate only if they share the same box. So you can have multiple processes sharing the same box and indirectly communicating. That's how people they go out to websites maybe and they go, oh look, there's an update. The system, the building is still on fire. Okay. And you get your information that way instead of somebody personally calling you up and telling you the building's on fire. Or you coming over and looking at it and going, oh, the building's on fire. Which actually demonstrates all the different forms of communication. But properties of the communication link, if the link is established only if processes share the common mailbox, it can be associated with many different processes. Each process pair of processes may share several different communication links. So. And the links might be bidirectional or they might be unidirectional. Operations, so create a new mailbox, send and receive messages through the mailbox. So these are things you'd have to program. These are things you'd write in your program for your processes to use. Destroy the mailbox. Primitives might be a send a message or receive a message, stuff like that. In terms of mailbox sharing, P1 and P2 and P3 might share mailbox A. P1 sends, P2 and P3 receive from mailbox A. Who gets the message? Both of them. Everybody gets the message. In terms of a solution, you can allow the link to be associated with at most two processes, or allow only one process at a time to execute a receive operation, so only one of them gets it instead of both of them get it. Or allow the system to select arbitrarily who the receiver is going to be and assign it to somebody in the box. Here, this one's for you. That one's for you. Or the sender is notified who has received it. We sent it to ITU, and B. Hacker signed for it in room 102. Oh, okay. That's where the message went to. Yeah, so they get the receiver knows who signed for it. It's kind of like receiving, confirmation. Synchronization in Java, it's really easy. You just put the keyword synchronize next to everything. Java actually creates a really nice multi-programmed environment for threads. In Unix, Linux, you have to do it all manually. In terms of synchronization, the word means that the messages are passing, and they're either blocking or they're not blocking each other. So if you have a consumer and a receiver, a consumer and a producer, they could be synchronized. So they're both working simultaneously, or one can work and then the other one can work. If they're blocking, only one thread is running at a time, and one thread blocks the other thread. So one says, okay, you gotta stop working because I need to work. Which, blocking comes in handy for certain things if we're looking at a shared resource. If you're both sharing, two processes are sharing the same resource, maybe you only want one of them at a time updating it, if it's data or something like that. So blocking is considered synchronous, non-blocking is asynchronous. So blocking, the block sending has the sender block until the message is received, and then the block receiving has the receiver blocked until the message is available. In a non-blocking scenario, it's asynchronous. The non-blocking sends, the sender sends the message and then continues. It doesn't block, doesn't stop working. And non-blocking receive has a receiver that receives a valid message or null. It doesn't get anything or gets a valid message. It just keeps receiving. It doesn't wait. So, in a perfect world, I think things run a little faster in a synchronous fashion, but asynchronous might be good for protecting data, protecting shared memory resources. And then we also have this concept of buffering that comes into place to buffer the memory between both of the simultaneously running processes. Queues of messages attached to a link, implemented in one of three ways, perhaps, with a zero capacity, the bounded capacity, or the unbounded capacity. And the buffering is an example of that consumer-producer with the shared buffer is a buffering example in terms of the communication. So essentially, what I just gave you is the foundational material for interprocess communication and the process concept. The next lecture, I still have a couple more slides on this lecture, but we're going to talk a little bit more about interprocess communication as go through some of the different scenarios outside of producer and consumer. I'm also going to hit the concept of threads, but I won't touch threads till next week. So, in terms of applying the processing model to different forms of communication, we have client-server communication that works with sockets. We have remote procedure calls, RMI. Excuse me, RMI is the last one here. Remote method invocation for Java. Remote procedure calls is more of a Unix platform protocol. These are different abstractions for processes that are communicating with each other, whether they're bound to sockets, whether they're running through software that's facilitating shared communication, or they're running through a Java JVM environment, actually, are the differences. In terms of the socket abstraction, the socket that's created is defined by an endpoint of the communication. So we have a socket at the host, we have a socket at the receiver, client to server. It's classic client-server type of behavior where many clients attached to servers through sockets. It's a concatenation of an IP address and a port. We bind them via a process, and then the processes essentially go out to the port and they send and they receive the information that's needed between the two. So the communication consists of pairs of sockets that work between the two. And here's our socket picture. So we have host X with web server, and we have a link, communication link that's created between them. This socket's actually running over IP, so it's not really a complete socket. This is essentially describing an IP protocol as well, which is the internet. So when you connect to the internet, you're not opening it. Well, abstractly, you're not using a socket. You're using more of a TCP/IP connection versus a socket abstraction. Another one would be RPC, which is kind of old actually. A remote procedure call is still being used today, however. So are sockets actually for certain things. You don't use the sockets actually, or primitive instant messaging programs use sockets, and so do some specialized like applications that are run on local computers that aren't on the internet but are using the internet. So they're usually going through ports and sockets. Remote procedure call, abstraction calls between processes or network systems. The stub, that's the client-side proxy of the actual procedure on the server that's being run. The client-side stub locates the server and marshals the parameters. And the server-side stub receives this message, unpacks the marshaled parameters, and performs a procedure on the server. It's another yet abstraction to the client-server communication that allows us to send and receive information back and forth. This one's using a marshalling concept with a stub, which is kind of interesting because this RPC is kind of what RMI is built off of, actually. The execution of it, way over here is the client. It's hard you can see it over here, but it says client. That says server over there, and the messages that are flowing in between via the proxy that's going on between the two computers. So, RPC is just nothing more than the protocols that are being used to facilitate the communication. Another very, very, very popular one these days is RMI. Remote method invocation is a mechanism similar to RPC's. It's most similar to that. It doesn't really use a socket abstraction. It allows one Java program on one machine to evoke a method of an object on another machine. So we have a bunch of objects over here. We have a bunch of objects over here. One object over here goes over here and says, hey, runs methods from each other, which is essentially what Java is doing. If you're not familiar with object-oriented programming, that's not going to help you. But objects are created, and then the objects communicate with other objects. RMI just facilitates communication over remote, which is where we get the remote method invocation. An object over here goes over here and says, hey, or this is the Java program, this is the remote object. It goes this way and says, hey, can you make an instance of this object for me? And the server says, oh, no, I already have it, here it is. It serves it up, or it just says, hey. So we only have one object running, and all the clients are sharing it. So it makes better use of object technology. And this is, again, just like RPC, it's another environment. Call it middleware, call it software, something you're loading on top of the operating system to give you a better managed communication between multiple processes that are running. Marshalling parameters, you also have the marshalling concept with JVM and the RMI module as well. So we have the client with a remote object. It's just nothing more than packaging of a message, sending it over, and unpackaging it. Passing the information from the stub to the skeleton back and forth. And no, I don't expect you to know everything about RMI after that, or RPC, or socket communication. But that was put in there as an example to show you different forms of process communication that happen in a networked environment. Everything else that I was talking about in this lecture would apply towards a single computer, single running operating system in a non-networked environment. However, we can take the process concept and extend it out into networking. When we do that, then we're looking at RMI, RPC stuff. So RMI, I would say, is probably the most current, more commonly used protocols these days. Doesn't have to be. There's other protocols out there as well. So that was chapter 3. And went through the concept of processes. So what we're going to do next time is go over chapter 4, which is going to be on threads. Questions? Comments? We still have a few more minutes. I can talk about the assignments if you want, or I can do them next time. Take a few minutes. Let's see if I have internet access, actually. That's the big question. Yep, I do. Very good. Let's take a few minutes here. We still got a few minutes. In this course, we have our syllabus. We have programming assignments 1 through 5. We have number 1. Probably not a bad idea to be doing number 1. Number 1 is going to be, some of them are writing assignments, some of them are programs. I'm actually going to download all of them while I have them. We don't have a midterm in this course, I don't think. Let's take a look real quick. Just regroup for a second here. Let's take a look at 200%. Make this thing bigger. There is no midterm for this course. We have those 5 assignments. This will be loaded up into the EMS within the next couple weeks. I don't believe anything is in there yet. We have this assignment. That's 50% of your grade, so you want to do the assignments. The other part is a in-class final exam, which will be multiple choice. The other part is the CSLO essay, which is a writing assignment. It's a piece of cake. It's not hard at all. So the bulk of your grade for the course is in those 5 assignments. And let's just take a look at assignment number 1 so you can get a feel for what I was talking about. And the lecture I just did today is pretty much the basis for assignment number 1, and it's the chapter that you want to look at in the book to do it. And what you're going to do in assignment number 1 is you're going to create this thing called a tiny shell. You're going to fork a process, and you're going to make a child process to run programs. So your shell, what you're doing is you're creating this small program to run different programs in the foreground and in the background. It's kind of like when you go to the shell. You can do it on a Windows system if you use Unix emulator kind of software. You can do it on a Linux platform. You can write it on a Mac, use a terminal, and do anything you want, essentially. Make it work in any way you want. If you do it on a Windows system and you don't have a Unix or a Linux type of platform, you might not be able to do this in C. What I mean platform meaning the capability of creating a process, which is impossible on a Windows system. You may do it in Java. Java will allow you to program in processes, and you can simulate this in Java. Probably more work than you'd expect, though. A little bit easier if you do it in C, but you have to be able to create a process. And most of the C libraries, unless you get an emulator for a Linux environment, Windows, Visual C++, not going to do it for you. If you have a MacBook, however, you can do it with Xcode, no problem. All right, so the objective is to create this program called a tiny shell, just like any other shell. In fact, here's a shell here. This is a shell. It's a terminal prompt where you can type commands in. One of the commands I'm going to type in, actually, let's make this bigger. I can type in ls, to get a list of stuff. I can type in ps to get a list of processes that are running. Or I can type in exit to exit out of the shell. So what you're doing is doing one of those programs, creating a terminal prompt window, or a shell window. So in the assignment, your assignment is to build Tish, which is a tiny shell, because it doesn't have that much functionality, to implement the following shell services: to run programs in the foreground and in the background, to list all of the processes that are currently running in the background, and to kill a process running in the background. So there's actually all the functionality is given for you. If I were in this shell, for example, all I have to do is run ps, and it gives me a list of running programs. All I have to do actually is type in ls, let's say -l with an ampersand. Just put an ampersand, I believe it's at the end, but well, it's supposed to run it in the background, but it's not going to run it in the background because it just ran it quickly. The output came this way. But using an ampersand to run a program in the background versus the foreground, and then killing a process, you can actually say kill space the name of the process to kill a process. So all of these commands are actually built in, which is why I said it's tremendously easy to do it on a Linux or Unix system, or on a Mac system where you have BSD Unix. Because you can use the built-in commands, you do not have to reinvent the wheel. So the precise requirements are as follows. Your shell should give the user a prompt. So I have to figure out how to do the prompt. You're basically going to fork off a process. You're going to start a program up that basically creates an endless loop that accepts commands. And it's going to give you this as a prompt, which is kind of easy actually to put together. And there's 2 types of commands. You're going to have internal and external commands. External commands are going to run programs. So you can say, run ls. or when you type in ls, it should take ls and say, well, it's not an internal command, it must be an external one, and then run an exec along and send it the ls, or whatever the command it is that you want to run, and it would essentially fork off a child process and run. Or we have the internal commands, which are the built-in ones, and as an example, by, which could be a wrapper for exit to end it, and then any of the other commands that are listed below here. And you can read through the description, but what I wanted to tell you about it was you can implement it in any language that you want. You didn't have to do it in C. If you're going to do it in C, I'd recommend following the assignment description. It makes it a lot easier. And the assignment description gives you a list of the internal commands, by, jobs, kill, which pretty much match the external ones. So you can, essentially use a wrapper on existing commands, and feel free to use something that's already in existence. There's some recommendations down here for using fork, exec. You may or may not, it might be pfork, it might be a different version of exec, vp might be lp or something. The libraries might be different depending upon your compiler and the platform that you're writing this on. Here's a little system call information. These are some system calls that are part. You may also use the stdio library as well. You can use anything you want. You don't have to use what's specified in the assignment description. That's what I'm saying. If you have a copy of the textbook, there's examples in there as well that would help you significantly. The next assignment, number 2, I'm not going to go over it. I just want to see what it's on. It's a little bit easier. It's on CPU scheduling, chapter 5. So right now in the course, you want to be probably doing assignment number 1 to get that over with, and then 2 is going to be on CPU scheduling. Number 3, I think, is going to be answering questions or something. Process synchronization. Actually, you're writing a CP program to copy one file to another file using the consumer producer example. And you can do that in any language you want. Any of the programs that you write in this course can be done in any language. And what I'm trying to do is get to the easy ones. Deadlock, well, you have to write a program here too. I know a couple of them I put in there were just answering questions. So the deadlock avoidance one is not too bad either. And the 5th one, maybe I don't have it in there. This is a paper. Okay, so the last one is a paper. Here it's a written report on the differences between memory. We haven't talked about memory yet, but internal memory, external fragmentation, internal fragmentation, main memory, physical memory, stuff like that. So only one of the assignments is really a report. The other ones are small programs that you're writing. So I hope you're familiar with programming. If any student does not like to program, I could possibly, although I don't prefer it, I could possibly come up with some alternative assignments for you. I would rather see you do something productive versus cheating. So before you start thinking about, how am I going to get that done? Am I going to have to copy somebody else's program? Before you do that, come and talk to me about it, or send me an email message and say these programs are a problem, and I can come up with a substitute way for you to earn those credit, because it is 50% of your grade. You don't want to just leave it and not do anything. So, but come to me in the next week or so and let me know that that's a problem for you. You've just switched majors and you're not a computer science major. If you have just switched majors, then that might be good practice. Especially if you want to be a computer science major. Not a bad idea to learn how to program in some language. So, questions, comments, or concerns before we end for today? Quiet group today. Nice. Nope, we're done. We're done. Computer graphics in about a half hour. No, 15 minutes. Okay, we're done.